this was in 2001, E18, across in the town named AS. And this was between Oslo and Sweden. And Webbed on Sands was the name. Selberg, Kunet Selberg was the architect whom he took the sketch to, and ultimately it was built by the Moulin Group, 100-meter span. Now, this is something else. But if you trace the history, they wanted to cross wide crossings. There was no technology to do that, so they had the idea of building 3-tier arches. The first one you can see is doing what, the second one sits on top of this, the third one takes it over shorter spans. They took the aqueduct with a road surface on top across the big water body without today's modern technology or either design, analysis, design or construction. This is the famous Pont du Gard near Nimes, road, bridge and aqueduct. Then this, again old one, this is the family of stone arches across the Seine in Paris. You can see the harmony, you can see the environmental invasion is nil, and it blends so well with the background. Then you have this famous Loire Bridge in Blois in France again. Very simple, but see the beauty of without interfering with the background. Then this one, Pont du Clerc, or the Lot River, 2-hinged arches. Incidentally, I was also in Pakistan. When I showed this, the minister who was an engineer, I don't know where he is now, Afghanistan probably, he said, how is this? Is it a 2-storied bridge, one below, one on top? It's just a reflection. It's a good photograph, that's all. Then we have this famous Professor Maynard across the Salina Gorge in Switzerland, 1930, reinforced concrete, hinged arch, 2-hinged arch. This is, we have to see it and you just fall on your knees when you look at it. It is absolutely music frozen in space. It just so very nicely fits the background, and you can imagine when it is all snows, how beautiful it must look. 90-meter span, 1930, Professor Robert Maillard, Switzerland. Then you have subsequently engineer Christian Menn. He's built this Via Mala Bridge. He's one of the greatest analysts of the modern times. Now, he had this job and he built an arch. He analyzed, designed and detailed and built this arch, supervised the construction, which blends so well with the background. You compare that with the monstrosities we have in Delhi. You will close your eyes when you come to Delhi and see them. Now see how this, there was once a study conducted by the World Bank, the effect on the human psyche of the hundreds of flyovers, concrete monsters that are being built in the urban ambience. And the result was that when you look at things like what you see in Delhi, it is almost certain that it will reduce the lifespan of those who look at it every day, compared to those like these which will increase your lifespan. It is as simple as that. Right now I am working on a project which is climate change effect on bridges. Climate change effect on bridges. And we did design the Saudi Bahrain for 30 centimeter rise in sea level. We did everything, it's built, but it is wrong. Today the estimate is upwards of 1 meter. But this is all conjecture, nobody really can analyze that. But be that as it may. Then you have this Rio, Canimar in Cuba. Now Cuba, as you know, is very humid and very warm. There is no winter. They wanted the bridge which would give you the feeling of openness. You know, you can breathe, no claustrophobia. So you see how the structural elements were put to the good use so that you never get that feeling. It looks all open. But this is one major step in the development of the history of bridges. And go on saying, there's a lot I will show you. This was a competition. It's in the island of Kirk in ex-Yugoslavia. Now Yugoslavia has broken into 3 countries. I was there for almost a year. This was a competition. They wanted to build these connections between one side and the other. I don't know if it works. Yes. Oh, I don't, yeah. Yes. So, I can't work with this. this side to that side. This was a global competition. The idea was not to hurt the environment and to make it look that would just beautifully fit the background. And this competition, this is a photograph taken by air. You can see how beautifully it fits in. It just merges with the background of the rocks. It is not just you start your calculations and analysis. You have to do a lot on environment and on the aesthetics part, which is because these will be things that will be left for centuries. Well, one hopes for at least a century, if not longer. While stone and timber remained the common building materials for bridges, the mid-19th century demanded stronger and bigger bridges over the large rivers for railways. So around 1840, the transition from timber to steel began. In this period, cast iron and later wrought iron was tried out by bridge builders. Now, cast iron being reasonably good in compression but no good in tension, this could not allow longer spans. Later, when wrought iron was brought into existence, the two were combined so that wrought iron could give you tensile members so you could go in for longer spans. This is another big step in the history of development of bridges. And the first recorded use of iron, the word is iron here, not steel, in bridges was a chain bridge built in 1734 by the German army across the Oder River in Prussia. However, cast iron was not found very suitable for building large span bridges due to its low tensile strength, as I just mentioned, and a combination of cast iron for compression members and wrought iron for tension members. This was used for truss bridges in 1840. And in 1856, just about 1 year before the War of Independence in this country, you are feeling very sleepy. I can see you yawning. I can see all your gullet. Please don't do that. In 1856, Bessemer patented a process for making large quantities of steel. This gave a fillip to the construction of bridges for long spans. And then followed by Simons and Martin, they introduced the open hearth process. In the last part of the 19th century, the new material, steel, caught the imagination of the bridge builders. And the first of fourth, first means a finger of C going inland. That's the first in Scottish language, which is not exactly English language. And Forth is the name of the place. So that place, a bridge was to be built across the Firth. This was a cantilever bridge of 520 meter span. Or then there was the Brooklyn Bridge, Roybelling suspension bridge of 490 meters in New York. These were a few of the famous achievements in the 19th century to mark the beginning of modern era of bridges in steel. This is the Firth of Forth Bridge. When you see it broadside on, it speaks to you. You can see the flow of stresses. You can see it is simply telling you how it is built. It's a cantilever construction simply supported, believe it or not. Then subsequently, a new bridge has been built, which is by the side, and I have tried to take a slide which will merge the two so you can see the old and the new. You can see the two in the lower. This one I make a mistake. I don't know whether I'm able to do it right or not. Yes, this is the one I was just telling you. This is the new one that's been built. The old and the new together. This is the old one, and this is that old one. This is the new one. This is the old and the new, the Firth Road. I would like to spend a little more time, but I don't have time. The director has to leave. Then this is the new Forth Road Bridge in Scotland. In the background, you see the old one. Now, one thing I want you to remember and mark, because we will be coming back to this, in the suspension bridge, we have these monsters called, these are steel girders, essentially to control the aerodynamic behavior or misbehavior of the bridge. These ugly steel trusses, they can be 30, 40 feet, 10, 12, 15 meters deep. And in fact, later Professor Leonard surmised that they are actually bad because they collect the wind force at the nodal points, which further displaces it against the aerodynamic stability. But be that as it may, we'll come to this. And you can see the suspenders are all vertical. Now, you remember this. These are all, as usual in a suspension bridge. The later, I'll come to that. The later tendency is to incline the suspenders so that you can get the effect of the truss action from them as well for the stability of the bridge. I'll explain that. Just hold on. By the turn of the 19th century, the growing use and availability of structural steel and greater skills in analysis, in design and in construction methods paved the way for longer span bridges. Multiple span girder bridges, arch bridges and cantilever bridges in steel reached very long spans with comparative ease then. Howrah Bridge, our own, 1943, designed by Rendell, Palmer and Tritton of England, a steel cantilever bridge with a total length of 457 meters, is a typical example of the large crop of outstanding bridges built in steel in the earlier years of the last century, but it is a bewildering mass. It is optimal quantity-wise. Some people like its shape, some people don't like. It is an absolute bewildering mass because it carries rail traffic, road traffic, millions of people. You have to see it to believe it. Many of you must have seen it. A very substantial advance in the understanding of the theoretical analysis of the load response of the structural system of suspension bridges was made by the 20s of the last century. Many elegant bridges were built, like Lindenthal's Manhattan Bridge 1909 with 450 meter span, followed by Steinmann's 340 meter span Florianopolis Bridge in South America, and the Delaware River Bridge of 530 meter span in 1926, to name only a few. By the way, Steinmann's bridge of 340 meters that he was given the commission to do the analysis, design, detailing, and then supervise the construction. But as a student at New York, this was the very bridge that was his project, which he submitted and got his letters. Then later, in practice, he was given the same bridge to actually do which he did, and I will show you that. The big leap forward came in 1931 with the construction of the George Washington Bridge in New York City, which has been acclaimed by no less than the great Stussy, one of the very great engineers. He said of this bridge, he said, and this is translated from French, the most important step in the evolution of art and culture of bridge engineering. This is exact translation, therefore it suffers a little bit, but I didn't want to touch it. It is exactly the translation of what he has said. And then the great Le Corbusier, who has designed Chandigarh, who was his friend, he was so enchanted with this bridge of George Washington, the George Washington Bridge, that in his 1937 publication, which was titled When Cathedrals Were White, he quipped, "The George Washington Bridge is the most beautiful bridge in the world. It is blessed. It's the seat of grace." Such comments coming from these big legends. This bridge broke the 1,000-meter span barrier, and its span length of 1,060 was double that of Delaware Bridge, which was 540, the then longest span in the world. The bridge was built by Amann, a Swiss engineer who migrated to America in 1904. Another great bridge engineer, master builder, master designer. 3 decades later, this foremost bridge builder in the world contributed his last great masterpiece to the land of his adoption states, named Verrazano Narrows Bridge. Amann's Verrazano Narrows Bridge in New York was opened in 1964, 10 months before he died, standing with a main span of 1,300 meters. The bridge is a landmark in the history of long-span suspension bridges. And this is the bridge. But you can see the stiffening trusses here as well, which nowadays people don't do. But I'll come to that because it's history we're talking. The lessons in ensuring the aerodynamic stability were learnt in a hard way by the tragedy of the 855-meter Tacoma Narrows Bridge, which fluttered and perished in 1940 in a 64-kilometer-per-hour wind. After we're done, because the director has to go, I would like to show you a small video clip of that actual failure. And the reason is not that people were ready to see it fall. They had gone there to enjoy their holiday. It used to flutter in the slowest of the winds. It crashed into the Sound. Sound is the lake. At a wind speed of only 64 kilometers, 40 miles per hour. But it used to do this all the time. It was nicknamed Dancing Gertie. Gertie is the name of the girl. People used to go there on Sundays, have their beer, have their sandwiches and take photographs. And one day this happened and the wind crossed that and the whole thing came crashing down. You might have seen, but I like to show you, if I can, at the end, the video clip of the actual failure of the entire long bridge. This is only a part of that. This is the end part of it. I'll show you that because I have it. I'll copy it and show you later. This is the one which I will show you. Professor Leonhardt, the great man, Fritz Leonhardt, he worked under Hitler and built a lot of bridges for him, but he claimed all the time that he had nothing to do with the Third Reich. But a great analyst, a greater designer, the greatest detailer. He is the one who proved that detailing in the drawing is much more important than all the analysis in the world. His idea was to prevent the creation of wind forces which cause the dangerous oscillations and not to counter them by putting this additional stiffness by these big stiffening trusses, which even increase the wind loads at their nodal points. This can be realized by aerodynamics, that's the aerofoil shaping of the bridge deck cross section, so that the wind stream hitting it broadside on cannot form the eddies. And this is the great man, died. Simultaneously, the reaction forces caused by the wind, the static wind loads, can be reduced considerably.